Good morning. My name is Woody. I'm glad to be here today and thankful to have the opportunity to present our latest effort. The title of our paper is Data-Driven Optimization for Police Districting in South Fulton, Georgia. This is a joint work with Alex Le, Professor Wang, Professor Shi, and South Fulton Police Department. Before we officially started, I'd like to give you some background about the city and its police force. First of all, South Fulton is the third largest city in Fulton County, Georgia, United States, near the Atlanta metropolitan area. It was incorporated in 2017 from parts of the southwest of Fulton County and consists of the 9 local communities. And it has a population of 99,000 and an area of 85 square miles. Since then, with the passage of the South Fulton referendum in 2016, Fulton County became the first county in Georgia with no unincorporated residential areas. As a result, in 2017, Fulton County also became the first county in Georgia to cease providing municipal services such as fire, police, zoning, and code enforcement. So many of the former Fulton County personnel and facilities were transferred to the city of South Fulton, and the city has started to create their own police system. So as the major law enforcement agency, SFPD has about 117 police officers that perform a myriad of service from responding to emergency and non-emergency calls for service, investigating crimes committed against persons and the property, conducting specialized investigations and crimes. So as you can see, the service region is evenly divided into 7 police beats or precincts. Each beat has the same amount of the police officer and they operate independently. However, a bad news is the design of the police districting in South Fulton area has never been changed since 1970s, almost 5 decades ago. In the meantime, the area has been undergoing a tremendous urban growth that drastically shifted its landscape. The U.S. Census Bureau estimated that the population of South Fulton has increased by 13.7% from 2010 to 2018. This has led to a significant increase in police workload, which is also exacerbated by the hardship in officer recruitment and the retention faced by the SFPD. Most importantly, demographic and traffic pattern change also create and unbalance the workload among different regions. The figure on the right shows the distribution of the 911 calls, which we estimated from 911 calls per service data provided by the SFPD from 2018 to 2019. We can clearly see that the certain beat faced a significantly higher workload than others. For example, police officers in the southeastern area of the city respond to many more calls than those in the western area. Therefore, it is clear that the current beat configuration has become outdated. So in the middle of 2019, the SFPD reached out to us. They was hoping that we can probably give them more insights about the beat design by taking advantage of the power of the big data. So from 2019 to early 2020, our team closely work with the SFPD to improve their police operation efficiency. Our project specifically focused on redesigning bit configuration by completely redrawing the boundaries and changing the name of the bits. And we aim to rebalance the workload of SFPD officers. So first, we need to understand the process of a local police operation and how it relates to the police workload. Typically, for each beat and each shift, there's one response unit, which is one police car with one or two police officers who are responsible to respond to the all 911 calls in that beat. So if the response unit is busy handling another incident, nearby available response unit may be dispatched to answer the call by the operator. And here's an example of the 911 calls per service. When a 911 call, for example, like a traffic incident comes in at a call time, a new incident record will be created at the dispatch center, and the call location will be also recorded. The operator assigns an officer to handle the call, and then when the unit arrives the scene, and then he can start the investigation. Once the police complete the investigation and clear the incident, the police report will be closed and the recorded clear time. The time interval that it takes the police to process the call between the dispatch time and the clear time is usually called the police workload. Okay, now let's dive into the methodological part of this project. And in this project, we redesigned the police patrol beats in the city of South Fulton using a data-driven optimization approach. The outline of our approach is summarized in this diagram. And our objective is trying to rebalance the police workload in each beat by redrawing the beat boundaries. First, we take advantage of the data from multiple sources, including GIS, demographic census, and the 911 calls for service data collected from the police reports. We then divided the geographic area of the city into more than 1,000 small geographical atoms and estimated workload in each atom using this collected data. And based on the workload estimation, we developed the statistical models to predict the police workload in the next few years. And lastly, the problem can be reformulated as a clustering problem, where each bit is formed with a cluster of atoms. And the optimal number of the bits is determined by a greedy exploration strategy. And the final design can be found by solving a mixed integer programming given the optimal number of bits. To be specific, the data source that have been utilized in this study, including the 911 calls for service, particularly the data in the first quarter of 2019, it usually contains the location of the call and the related timestamps, such as the call time, dispatch time, which can be later used to estimate the police workload. And the second one is the geographic data, or the GIS, provided by the government of the Fulton County, defines the boundary of the city and the corresponding current 7-bit. And the demographic census collected from the US Census Bureau is the third kind of the data that we have taken advantage in this study. So here we select around 20 census factors correlating city's socio-economic profile with the workload, which are particularly useful for us in making a prediction of future workload. And these factors contain essential information about the development and economic growth of the city. And as we mentioned earlier, to completely redesign the boundaries of the bits, we partition the entire region into 1,187 square geographic atoms. Each atom has an area of 0.346 square miles. And then, as shown in this illustration, our data can be reorganized and mapped into the grids accordingly. For example, we can calculate the number of the calls occurred in each one of these atoms and calculate the average travel time and average surface time for each one of the atoms. Similarly, we can do the same to the census data. The census was originally recorded by census block or zip code, which is usually much larger than the geographical atom we define. By performing a spatial interpolation, we can align the census data with the 1,000 atoms as well. And essentially, the arrival rate of non-Wang calls can be modeled by a spatially lagged regressor. Look at expression of the model. So lambda IL represents the non-Wang calls arrival rate in atom I at time t. This will be related to a noise term and three components, including the number of the calls in the neighboring atoms at time t, the past number of calls occurred in the same atom I, and the census data recorded in atom I in the recent history. And in the end, the police workload can be estimated by the non-Wang calls arrival rate times the sum of the average travel time plus the average service time. Here, we show the workload distribution in 2018 and its prediction in the next 2 years. We can observe that total police workload grows mildly while concentrating in the southeast of the city. Due to the increasing growth of the South Fulton and urban sprawl, this trend is certainly leading to a police workload imbalance. And as we mentioned previously, when creating a bit design, the most important thing is we have to define the number of the bit first. So here we perform an iterative greedy algorithm, which attempts to generate a new bit greedily for the design at each iteration, while preserving the original structure of the existing bit as much as possible. We started with current 7-bit design by dividing the bit with the largest predictive workload and iterated the process, so on and so forth. And intuitively, as you can imagine, more bits may result in a more balanced workload distribution, as we can clearly tell from these figures. And for determining the optimal number of the bits in the design, we also need to consider the cost associated with adding more bits, which includes the cost of additional training, hiring new officers, and so on. However, the manpower of the SFPD and the resources of the South Fulton City Council are usually limited. It is unrealistic to deploy such a design with a large number of bits. Therefore, there's clearly a trade-off to minimize the workload variance while avoiding unnecessary costs for adding new bits. So here, the left shows the average workload is decreasing as the number of the bits grows, and the right shows the variance has a similar decreasing pattern, whereas the benefits of adding more bits is diminishing rapidly when it is larger than 15. After rounds of discussion with the police chief and other police officers and showing them the analytical results, we eventually decided to have 15 bits in our final plan. And given the optimal number of bits and the bit design created by the greedy search, the problem can be reformulated as a mixed integer programming where the decision variable is denoted by dik. It equals to 1 if atom I is assigned to bit k. Then the objective is to, let's say, minimize the workload variance across the bits, while we also need to ensure the contiguity and compactness for each one of these bits. However, in this case, we have more than 21 million continuous variables, and 35,000 binary variables, as well as a set of additional linear constraints as needed to be satisfied. So in practice, the problem itself of searching for a global optimum design is computationally intractable and hard to be implemented on a large scale. So to tackle the computational issue, we propose a heuristic method to search for local optimal design at a reasonable computational cost. Specifically, we adopted as the simulated annealing algorithm to implement our heuristic search, where at each iteration, we can find a better solution with possibly lower police workload variance in its neighborhood. The last accepted candidate solution when the algorithm stops will be considered as the refined bit design. And now let's look at these tables. So we have shown the predicted police workload for of each bit and the original bit design and the new design. We have seen there's a drastic drop in the workload variance by roughly 90% after redesigning the bit configuration. Comparing to the design suggested by the greedy algorithm, we also see about 7% improvement in the final refined bit redesign. And here are the layout of the previous bit configuration and our new design with 15 bits. Our redistricting plan mainly changing 4 areas. We added 3 new bits in the southeast of the city near College Park, the area with the highest workload. The biggest bit in the west of the city is split into 2 bits. We also add a bit in the north of the city near the airport, and the southern bit is also split into 2. So in total, the redistricting plan has reduced the response time throughout the city and rebalanced the police workload between the 15 bits. And lastly, in terms of the implementation, in January 2020, we submitted the final report to the South Fulton Police Department and the South Fulton City Council. The report was reviewed by the Police Chief Meadows, Deputy Chief Rogers, and the Mayor Bill Edwards. And later that month, the South Fulton City Council approved the new bit design, and later that year, the SFPD officially implemented the new districting plan. And to be honest, we don't like to brag about it, but as a matter of fact, our plan was praised by the City Council, as some member said that our bit design and the study has long been needed, and it sets an example for other cities in the Southwest. Residents of the South Fulton also acclaim about change on social media, and of course, thank the SFPD and our team for contributing to the communities. And we also recognize that the new bit design also received the media coverage from several news sources, including the Foxfire Atlanta. So as a summary, we presented our work on the City of South Fulton zone police zone redesign in this presentation. We first proposed a computational framework with large-scale data nets, which construct a statistical model to predict the bit workload, and explore the number of the bits by a greedy search. And in the end, we solve a large-scale optimization problem by a heuristic algorithm. The proposed redesign has been officially implemented by SFPD in 2020. And we also want to emphasize that we used a similar framework to help Atlanta, which is the largest city in Georgia, to redesign its zone configuration. That's all for my presentation. Thank you.